In this video, we demonstrate a new technique to confirm oocyte penetration and viability. There is a challenge with automated ICSI systems. Image processing algorithms are still unreliable and therefore lead to low fertilization rates. Biological membranes act as small electrical resistors to the movement of ions in and out of the cell. Electrical resistance of the ICSI pipette tip can be measured using electrophysiological equipment. When advancing the ICSI pipette into a viable cell that has an intact membrane, a resistance increase should be detected. During early apoptosis or necrosis, there is a formation of membrane pores that allow free movement of ions in and out of the cell. These pores can be visualized by electron microscopy but not by light microscopy. Penetrating an egg in early apoptosis will show a small or no resistance increase, although the egg may still look viable through the microscope. In late apoptosis or necrosis, the membrane is already fragmented, and that can be easily visualized with light microscopy. In this case, resistance measurements have no advantage. As in any other biological cell, the oolemma has an electrical resistance created by the phospholipid bilayer. During ICSI, an electrical circuit can be formed between the ICSI pipette and the holding pipette, in which case both pipettes have electrical resistances. When ionic current is passed through the ICSI pipette into the holding pipette, the vast majority of the ionic current will flow around rather than through the oocyte, following the path with the least resistance. However, when the ICSI pipette tip is inserted into the oocyte, the ionic current is forced to flow through the oolemma. In this case, the natural resistance of the oolemma becomes a third major resistance component added to the electrical circuit. We hypothesized that an increase in electrical resistance can confirm oocyte penetration and viability. In order to measure resistance, we apply a constant voltage step that generates an ionic current. The resistance is calculated by dividing the applied voltage by the measured current. We tested mouse and human eggs. In order to measure electrical resistance in an ICSI system, we had to manufacture a specific adapter. This adapter integrates into the micropipette holders, the holding pipette and the ICSI pipette. The whole purpose of this adapter is to introduce an electrical wire into the micropipettes. In this video, you see the assembly of this adapter and its integration into the ICSI system. Picture A shows the adapters integrated into the pipette holders. The yellow arrow in picture B points to the portion of the electrical wire that is going to be inserted into the glass micropipettes, ICSI or holding. As proof of concept, we characterized the electrical resistance when piercing versus not piercing the oolemma. In order to do so, we applied positive pressure through the ICSI pipette. Penetrating the oocyte leads to a resistance increase, and rupturing the oolemma with high pressure results in an immediate resistance drop to baseline. In contrast to the previous video, the following video shows that there is no resistance increase if the oolemma is not pierced. The summary of the proof of concept experiments shows a significant resistance increase in the penetrated group only. The next step was to measure resistance change in oocytes with visually intact oolemma versus fragmented ones. In this video, we see an oocyte with visually intact oolemma. The large resistance increase confirms its viability. The retraction of the pipette drops the resistance back to its baseline. A fragmented oocyte is never viable and therefore will not show a significant resistance increase as shown here. In this experiment, the fragmented mouse oocytes showed a resistance increase of up to 2.2 megohms, and there was a significantly higher resistance increase in the oocytes with the visually intact oolemma. In step 3, we studied the electrical resistance change in human oocytes using a commercial ICSI system. In the top video, we see a large resistance increase when penetrating the oocyte with a visually intact oolemma. Please note that leaning against the oolemma does not result in a significant resistance increase. In the bottom video, the fragmented oocyte does not show a significant resistance increase, as in step 2. The summary of human oocyte experiments shows a small resistance increase of up to 0.3 megohms for the fragmented oocytes, and there was a significantly higher resistance increase in the oocytes with visually intact oolemma. Our limitations are that no human metaphase II oocytes were studied, nor their fertilization potential. In conclusion, we have developed a fully functional device that can be easily integrated into any ICSI system. The device measures electrical resistance in real time. When there is a significant resistance increase, both oolemma piercing and viability are confirmed independently of visualization. It is noteworthy that when there is a visually viable oocyte, but the resistance increase is relatively low, the oocyte might have not been penetrated, or it is not viable, or there is a large leak current. This device can be integrated into any cell injection system and therefore has the potential to improve the reliability and productivity of automated cell injection systems. Thank you for watching.